The next 3 lectures or so, 3 or 4 lectures, are dedicated to the design issues relating to a salient pole type machine, the Reluctance Synchronous motor. This is a motor configuration that it uses a stator from an induction motor and a special salient pole rotor. So what's all the fuss about these? These motors have been around for a long time, and there's so much interest in this type of machine lately. The principal reason is probably due to the rising costs and the limited availability of neodymium magnets the last couple of years. That might change. I suspect that the supply and demand issues will change to the point, and price pressures will change, and that will get back to normal. But in the meantime, there's a lot of interest in alternative machines, particularly for vehicle traction and appliances and a number of other important applications, that where the high cost of the magnets in recent months and years has messed up a few business plans. Business models don't work at those magnet prices, so alternatives are being looked at, and reluctance machines of 2 types are being considered. One type is the single salient pole type called Reluctance Synchronous machine, and the other one being considered is the dual salient pole type called switch reluctance. And what gave special importance or interest to the Reluctance Synchronous machine was the fact that ABB, a well-known large worldwide electric motor company, recently introduced a new product line that they've trademarked SRM, Synchronous Reluctance Machine. And they've released a complete product range from 17 kilowatts to 350 kilowatts. Now, they wouldn't have done that if there hadn't have been good reasons for them to do that. So let's study this machine, and let's look at some advantages and see what ABB has to say about this product line. The obvious advantages of this machine is that the cost to manufacture it is much lower than a PM machine, principally because there aren't any magnets in the rotor. And there's some other advantages, although there are very low losses in the rotor. PM machines are said to have low losses too, but they still have losses as well. And induction motors, of course, have with high torque density have losses from the currents in the rotor. And since the RSM has no conductors, why there's no ohmic losses. The manufacturing process of this machine is very simple, because for the stator, that's a major part of the motor. The stator, you use exact same stators as induction machines, so you use all your existing infrastructure and tooling for the stator and winding. This machine has pretty good field weakening capabilities to operate over a wide constant power range, and it has another sort of, no pun intended, salient advantage, in that it's synchronous in operating behavior, and so there's no slip. Its historical success is probably, you might ask, why hasn't it been historically successful, one might ask. Well, I think the answer to that are previous rotor designs did not produce sufficient saliency or sufficient ratio of inductance between the D-axis and the Q-axis to make these the power factor high enough, to make the efficiencies high enough to make these practical machines as replacements to induction or permanent magnet machines. And the secondary problem with them was that the rotor configurations weren't robust enough against the forces on the rotor that are required to sustain the torques it produces. So let's look at I mentioned the 2 choices of reluctance machines. Let's look at the 2 and kind of compare them a bit. The switch reluctance machines it requires brand new manufacturing technology, and everything about this machine is different. The rotor, the stator lambs, the windings, everything about it is different. The windings are special, not that they're that bad or complicated, they're just different than what a house that a house, meaning a plant that's used to making induction motors, is used to making. And the rotor of a switch reluctance machine is very robust and rugged. I heard someone say you could drop a switch reluctance motor off of a bridge. As long as you didn't Burnell the bearings, it would still run. There's no conductors on the rotor, so it's very robust, very rugged. And it will operate in high temperatures also. One of the drawbacks of it is that it's kind of noisy. It tends to be noisy because of the salient poles. There's a big attraction between the rotor and the stator when those salient poles line up, and when they misalign, when you turn the phases, they're attracted when they're aligned, but then they fly apart. The stator flies apart, so to speak, relative to the air gap anyway, when the phase that attracted the rotor is turned off, so it rings for a while and makes growling, obnoxious noises. But there's a way to control that, but that's one of its biggest drawbacks. Another big drawback is it requires a special inverter and control algorithm that's different than any other kind of machine, and that's very annoying to a lot of motor people and customers, so that's very special. Now on the other side, the Reluctance Synchronous machine uses standard AC stator, uses standard AC phase windings. It's a very simple rotor with no conductors, just like the switch reluctance. It's not quite as simple, but at least it doesn't have conductors. It exudes normal noises like an induction motor, nothing serious there. But one of its big advantages is it uses standard AC inverters with a change in software. Now that is really important. You don't need these special inverters or IGBT packaging topologies that you don't have to have special. Use standard ones that are low cost, and you've already got the drives. You don't have to invent them, and you don't have to figure out how to control this RSM, because you can control it with Q and D axis current control, which you're used to controlling for induction and IPM machines. Now, what the history of these goes way back. It's a very old motor. It goes way back, and I guess there was an original patent on this in 1923, it looks like. But there's basically two types. There's the rotor configuration that's laminated down the length of the shaft, and here's an example, and here's an example. And then there's the other type that's laminated radially coming out from the shaft. Now there's terminology difficulties with what you call this, but I'll clarify that a bit later. But these are the two configurations, and what you have to do to provide salience in there, you can see in this picture here, and we're going to look at a number of other pictures. That's an example as well. This part is called a flux carrier, a magnetic flux carrier, and there's another one. And this part here is called a flux barrier. This is a flux barrier, and this is a flux barrier, because these clear white parts are non-magnetic. Those could be made out of other materials. It could be air. It could even be a magnet, but that would be a shame to put magnets in this unit, because you're trying to get rid of magnets, even though magnets would improve the performance, but so what? But so you have these iron pieces that are flux carriers, and these flux barriers, magnetic barriers, normally air. And of course, you can make these with line start capability, but we're not interested in that here in this lecture. We're interested in inverter-driven versions of this to replace the permanent magnets. Now, so you see this version has layers of steel and layers of some insulator. This one is all steel, but it's punched in such a way that you have air passages. You can see that better here. Here's a flux carrier, and there's a barrier, and it's all stamped out of the hole of the stator. Now, to hold this thing together and give it some strength against radial centrifugal and tangential forces, you stamp this with some little webs. There's little webs here to hold these flux carriers together, and then here's a little web in here to hold the mass of these carriers against centrifugal force. Now, each one of those webs allows leakage, flux leakage. But one thing that's clear from these designs is the inductance is lower here than it is there. The saliency is in this pole where you have most of the flux carriers addressing the teeth of the stator to allow flux from generated in the stator to continue and flow in this direction to the next pole in the stator. So that's how it works. And the most recent designs, the evolution of this, the original ones were very poor. The newer ones, I guess, are much better. And ABB has a whole product line of these now. So as you could see, here's another typical cross section that we could study. Yeah, the stator is a standard induction motor stator. The rotor is configured in such a way to have flux carriers and barriers. Here's your direct quadrature axis is this way. Direct axis is that way. So since there's more iron in the circuit in this direction, you're going to have the phase is going to measure a higher open circuit inductance than it will in this direction, which has air passages blocking the flux. So this will give you a higher inductance ratio between the Q and the D axis configuration, and it increases by definition the saliency. The real strengths of these machines, as expounded by ABB and others, is there's no magnets. They're sinusoidal machines capable of delivering smooth output torque with very little ripple. They offer an opportunity for a very low-cost machine with a simple rotor using a lot of infrastructure that already exists. Now, what are the challenges? The challenges are designing the rotor to achieve saliency ratios that are high enough to assure that its performance can compete with well-designed induction machines or PM machines. Achieving this high saliency ratio requires an increase in the complexity of the rotor and a reduction of its structural integrity. So there's a dichotomy or a technical challenge, an opportunity for some very creative work that might even be patentable. Who knows? It's unlikely, probably, that this type of machine is going to challenge the performance metrics of PM machines, except if you put some low-cost permanent magnets in the flux barrier sections of the rotor. Now that hardly eliminates PMs, but it might you might be able to get enough performance out of an RSM by using some very low-cost bonded magnets in those flux barrier cavities. People have tried that and they're playing around with that, and that still might be a viable competitor to a PM machine. Here's a photograph that ABB provides. Here's a cross-section comparison. They're identical stator for both machines, and here's their induction rotor stator that you see up here in this photograph, and here's their RSM rotor. This is their induction rotor, not stator, die-cast aluminum. And here's their RSM. I presume this picture that I got off of their literature represents their configuration. It doesn't seem to. The shape of these flux barriers and carriers looks different than this picture, but and you might disregard that as insignificant, but my experience with designing these machines is that is not insignificant, that this version of this rotor, you see in that picture too, probably doesn't achieve the saliency ratio that does. I'm pretty sure that's true. See, you have steel right here. It goes all the way to the shaft, so flux is carried there, and there, and it's barred from being carried in these air sections. This rotor doesn't require much cooling like the induction does. It's got these cast fan blades on that helps it cool, and So the challenge is for us and anyone that wants to work on these is it's all in this rotor. The challenge is in the rotor, not the stator. Use an existing stator, existing inverter, and spend all your effort trying to design a rotor that will give you acceptable performance. The way the laminations are punched is exactly the same as the induction motor rotor. It's just a matter of changing the die punches after you come up with the right configuration. Here's some promotional things that have been presented to us by, this is public knowledge, by ABB. Traditional induction motor, if you take the total losses and you break this down, you have what does this say here? You have 60% of the losses are in the rotor for induction motor, and I guess, I'm not sure what this is saying here, but I guess it's that most of the losses are in the stator for the reluctance synchronous motor. That's what it's trying to say. Here's a better explanation of this. This is a plot of their product line, comparing their induction motor to their reluctance synchronous motor, going from 1 kilowatt up to 1,000 kilowatts, a megawatt. And they're plotting the efficiency versus the power. And as you can see, the efficiency goes up as the machine goes up, as you would expect for the induction motors this line, but they're projecting quite a bit of difference in the efficiency of the reluctance synchronous machine over the induction. And of course, as you would expect, the higher power you go, the closer they come together. That's true of every kind of machine. Higher power, the efficiency increases. So when you think about a machine like this as an optional motor for traction for a vehicle, here's some typical machines. Here's 6 machine types that are potential for traction vehicles, and traction seems to be very important these days. We've got new gas mileage standards set by the government, so that means that there are going to have to be a lot of hybrid or electric vehicles in the system. That's not to mention the electrification of off-road equipment. It used to be off-road equipment were powered by diesel engines through transmissions. The rail locomotion has been diesel-electric for many years, but even that is changing to do different kinds of traction machines, getting rid of DC commutated machines using induction or permanent magnet or reluctance machines. So all those things are potential forklift trucks and urban transit buses and all sorts of mass transportation systems. So we don't have a clear summary of the advantages or disadvantages of these. Here's the permanent magnet machine, surface mounted or inside mounted induction machine. Here's another form of the IPM, which allows you to use low-cost magnets, by the way, for flux squeezing, particularly an 8-pole version of this. And then here's the switch reluctance and the synchronous reluctance. So these two machines were included in this comparison for vehicles. IPMs currently dominate traction. Reluctance types use no magnets. SRMs are noisy, as we've said before, but so it certainly is attractive. We can see that. Here's a comparison done by this, I don't want to, Bogoletti, Aldo Bogoletti and IEEE and Pastorelli. These from University in Torino, and that's in the middle of the auto industry in Italy. So they did a thermal comparison of an IPM. Let's see, and an I'm not sure. I think this is supposed to be. This isn't an IPM. This is not an induction. This is an IPM. That's a mistake there. So anyway, this comparison was done in Italy with both motors using the same stator but with different rotors, and there's how you calculate the torque. Both motors had about the same air gap flux density and ohmic stator losses because they both use the same stator. Due mainly to zero rotor losses, the RSM machine was, I'm not sure what this is. I've got to go back and check. I guess this is not an IPM. This should be IM here. This is a typo. This is an induction motor versus an RSM comparison because the torque rating was 17% higher on the RSM version than was the induction rating, and was validated by testing. There's no data. Note that there's no data in that paper on the saliency ratio of that RSM motor, as how good it had to be to achieve that 17% higher torque value. Here's a cross-section comparison of an 8-pole reluctance synchronous and a 6-pole switch reluctance. So you could see this is a clear indication of what the cross-section of the machine differences look like. They're totally different. Here's your standard induction stator, totally different stator here and windings around each tooth, and of course the rotor is constructed with these salient poles. That's quite different. Here's another picture that compares them the same way, how simple the switch reluctance is, but different than anything we've ever done. And here's the reluctance synchronous with the standard stator and the flux carrier barrier rotor. Let's see. Some more comparison data here. This is probably, some of this is a little redundant, but this is a direct comparison between the RSM that covers things like that weren't on the other one. Is the frequencies are a problem, and small air gaps. Both of these motors require small air gaps, but perhaps the switch reluctance more so than the reluctance synchronous. But one of the problems with the switch reluctance is higher frequencies. At least the reluctance synchronous machine experiences the same core losses and frequencies as induction machines, whereas the switch reluctance produces much higher frequencies, so the lambs tend to have to be thinner. The switch reluctance is more robust than the synchronous reluctance. Here's a comparison of the inverter topology difference, and it's quite a bit different. The switch reluctance has the phases in parallel to each other between the DC rails. Assuming you have AC source here, you rectify it, and you have two DC rails. And in reality, these capacitors can't be over there. You have to have a cap right on top of the transistors, right across here. The cap has to be across here. It's got to be close proximity to the transistors, or because of inductance. And then, if you'll notice in the induction motor or the reluctance synchronous motor, there's a diode inside the transistor here that goes from the emitter to the collector, and that diode can't be used. There's one in these transistors too, but you can't use it because you have to have the diode connected like is shown here. So there are no standard, very few of any standard IGBT modules that have the diodes internally configured in this way for a switch reluctance. They're all configured for conventional induction and brushless machines. So that means that you have to use twice as many power components. If you have 6 transistors here with the diodes built in them, you got 6 transistors here for 3-phase, but you can't use the diodes built in them. So you can use 6 more transistors and use those diodes, because they are probably Schottky type diodes. But you basically, people add extra diodes. So that's a problem that can be overcome by volume, and it has been overcome by volume with switch reluctance for a number of applications, like the washing machine application. But for sure, with the RSMs, the big advantage, you don't have to worry about that. Use standard inverters. As stated earlier, these machines have been around for many years, but the power factor's always been so low and the efficiency's been low, so they've never been seriously considered. As I said, the key to improvements in efficiency and power factor lies in the inductance ratio or the salience ratio. And we're going to look at how to design rotors for that in subsequent lectures. But the potential advantages of using existing inverter technology and existing induction stators, frames, and manufacturing infrastructure with only a new rotor is very attractive to justify some R&D and development to see if a successful rotor can be designed. And it looks like ABB's already done that. The other issue that we should mention in passing here is the mechanical stability of the rotor. I touched on it earlier, but this is a nice picture, a blow-up view of the rotor configuration similar to ABB's. We want as this is a quadrature axis. We want the induction to be as low as possible there, and this is a d-axis. We want the induction to be as high as possible there, and all these leakage paths decrease the inductance in this axis. So, but these have to be maximized to hold this thing together. These support ribs have to be maximized. I guess you could pot this. You could fill this with epoxy or something like that, or maybe you could insert some kind of a bar in there, one for each pole, that you clamp somehow, have them stick out the end of the rotor and clamp them somehow to increase the robustness of this. And if you had something to fill these, if you filled these cavities with something, you could eliminate these altogether. You might even be able to eliminate those if you clamp this all together with something coming down the end. But I'm sure that's been thought of, but that gives you something to think about. That concludes this lecture. We'll look at the next one's how to design the rotors. Thank you.